Well, thanks, Joel. Just learned that name, beautiful name. All right, so very happy to be back. I was a member here myself a long time ago. Beautiful weather. I'm also happy that I give the talk today and not 3 days ago. 3 days ago, I was like this. I play tennis, I pull my back, I barely walk. I'm still a bit crooked, but I think I can. So I will be talking about this exponential sums on the multidimensional torus. S of x is the notation that I usually use. So what we have here, we have a bunch of frequencies that are lattice points. This notation E of z to the 2 pi I z. So here it is, and then you have a bunch of coefficients a sub n, which are complex numbers. And so this is an exponential sum. And I have some examples, just 2 of them for this talk. The lattice points on dilates of the sphere. So here you have the unit sphere in the d-1 dimensional one in RD. That is rescaled by a factor of square root of n is an integer. Look at the lattice points. Why are these exponential sums important? It's because they are the eigenfunctions for minus the Laplacian on the torus. All our eigenfunctions are of this form. So the eigen value corresponding to this is n, as you could easily compute by taking 2 derivatives. So these have been heavily studied. Then another example that I'm actually going to spend more time with is the example of the Weyl sums. Last night when I arrived here, I discovered that I'm camped on Weyl Street, not too far away from here. So there was an appropriate name for my visit. So the Weyl sums are the generalizations of the Gauss sums that you might be more familiar with. These are quadratic, but you can go any degree. Again, you can attach some coefficients if you want to make them harder, potentially much harder. And there's lots and lots of other examples. If you look at the solution for the Schrödinger equation on the torus, that's yet another example that can be written this way, but I'm not going to talk about that. What do you want to do with these exponential sums? Well, maybe you want to integrate them and see how big they are in average. And there's always something easy that you can teach in the first week of an undergraduate class of Fourier analysis, namely that you can square these sums, you can use orthogonality, and the L2 norm or L2 moment, as we call it, of these sums is actually computable. This is all equality here. How nice is that? This is equal to the L2 norm, little L2 norm of the sequence AN. That's the L2 theory. Nothing else is easy, as we soon shall discover. And you can ask the question about other moments. What happens, for example, for b greater than 2? You can only say that if p is greater than 2, because this is a complex space, 1, the norm only increases, but you don't know how much more it increases. Now, for Weyl sums, example number 2 on my slides, this problem of characterizing, of computing the LP norms of these sums has been known as, well, the main conjecture in the Vinogradov's mean value theorem. And it was asked sometime in the 30s by Vinogradov. There's lots of progress over the years, most notably Trevor Woolley, a number theorist, that used p-adic methods, you could call it p-adic harmonic analysis, to attack this problem. He solved it for d equals 3, and here's the theorem here at the bottom. And then Jean, Larry, and myself solved the problem in 2016 for all degrees using very different methods. Euclidean harmonic analysis. The specific method that we used is called decoupling. This name will appear a few times in my talk. And then after we solved the general case, Trevor also managed to update his methods, the so-called efficient congruency method, to actually get the same result himself. The arguments are not fundamentally different. There's lots of parallels between them, but they were initially formulated in slightly different languages. So anyways, what does the result say? The Vinogradov mean value theorem, as it's known these days, it says that there is square root cancellation in norm, namely for every p that's between 1 and this critical exponent p sub d, which is d times d plus 1, for every such p, the LP norm is in fact comparable up to n to the epsilon losses to the L2 norm, and the L2 norm is right here. In other words, apart from the potential of losing some logarithms, the LP norm doesn't increase with p in this range. And then something more dramatic happens for p larger than this critical exponent. You pick up positive power of n, but I won't talk about that. Any questions so far? So for Laplace eigenfunctions, the story is more complicated, and it's open even in the first interesting case in 3 dimensions, d equals 3. You'd expect square root cancellation in a certain range that I didn't write here. However, we only know square root cancellation in a smaller range. Why is the sphere more complicated than the moment curve, right? So all these frequencies lie on a certain manifold. In the case of the Weyl sums, they lie on the moment curve, t squared, t cubed, and so on. In this case, the frequencies lie on the sphere. Well, the lattice points on the moment curve are easy to grasp because every integer on the t-axis, if you wish, generates corresponding integer on the moment curve. So if you give me the integer 7 squared, 7 cubed is, the corresponding integer on the twisted cubic. There's no mechanism to generate the lattice points on the sphere. They are distributed in a funny way. There's regions on the sphere with large gaps where you don't get any lattice point, and then there's other caps where you do get the right distribution of lattice points. In some sense, there's missing points on the sphere, missing lattice points, and this creates a lot of number theoretic issues that we cannot address using just analysis. All right, now I talked about global bounds so far, right? So what happens if you give an exponential sum and if you integrate that sum on the torus? You could ask the question at the opposite end of the spectrum, what happens with the pointwise value of these exponential sums? Look at the individual points now, individual axes, and can you tell how large the sum is at that point? This is a difficult problem. There is a mechanism that has been known for a long time, which allows you to go from the Vinogradov mean value theorem listed here to some sort of pointwise bounds for the same sums for axes that are close to rationals, right? So if there is a Diophantine condition for xd, for example, you can come up with a sensible upper bound for the corresponding sum. And there are such pointwise bounds that follow from the Vinogradov mean value theorem. Interestingly, especially since this is a program in dynamics, I thought I would bring up this very recent result by Flaminio and Forni. They were able, just in February, 2 weeks ago or so, to obtain the same kind of pointwise estimates, the same kind of strength in terms of the exponent as we did as a consequence of Vinogradov, while they obtained it using dynamical methods, equidistribution of needle flows. And that's all I'm willing to say about this. If you're interested, have a look at their paper. It looks complicated to me, certainly not the language that I'm familiar with, but they do get exactly the same kind of exponent. We believe, it is believed that these bounds are not optimal in general. Many people believe there should be square root cancellation at pointwise level, and what we get here is not square root cancellation, but nobody knows. And it's a bit peculiar that completely different methods lead to the same exponent. So,
Ciprian,
yes.
You said you don't want to say any more about this, but you say equidistribution of needle flows would feel that it's enough to take just skew products. Do they?
Yeah,
really,
they take. I think they do.
it should be skew products rather than more general needle.
Yeah, I think.
Okay.
I have to go with your intuition. You're really right. I haven't looked at the paper in detail. But have a look at the paper. It's okay. It's interesting. It's long also. So as I said, these bounds are not optimal, and I advertise this as the opposite end of the spectrum. Looking at the global behavior on the torus, integration is somewhat easy. Understanding the restriction to points is difficult. So what lies in between? Well, here's one way of looking at the intermediate problem. So for the same kind of exponential sum, you may now consider a hypersurface lying inside the torus. So this is a d-dimensional manifold. See, it's smooth, nicely parametrized. It has this natural surface measure. You can think about a sphere, a plane, a curve. Well, a curve would not be a hypersurface unless it's two dimensions. But let's say a sphere, a plane, a cone, whatever we wish, a paraboloid. And then you can start asking questions of the following nature. You can say, can your exponential sum be large on sigma, on a large subset of sigma? Of course, sigma has a zero measure here. It's a very thin singular set. It can use a sigma that that captures somewhat consistently as you increase the dimension or change the coefficients. Consistently captures the large size of S of x. Do you have square root cancellation? This is a global statement. Well, global in the sense that you integrate, but only on the manifold. Square root cancellation means that the LP norm is still comparable or less than or equal in this case to the L2 norm. Equidistribution in my language would be the case when they're equivalent. And I would say that the questions for constant coefficients n equals 1 are already hard and interesting. Perhaps number theorists would be more interested in the case n equals 1. Oftentimes, our methods that use Euclidean harmonic analysis make no difference between the case n equals 1 and the arbitrary case. So we get the general case just as a natural byproduct of our theory. Good. Any questions? So the case, I have two examples. Let's start with the lattice points on the sphere, the eigenfunctions of the Laplacian. This is a fascinating example that has been investigated quite a lot about 10 years ago, I would say, by Bourgain and Rudnick. They have a sequence of very inspiring and sometimes long and complicated papers on the topic. They made a conjecture, and I'll talk about the motivation in a second. So the conjecture is fairly easy to state. You have a real analytic hypersurface in the torus, which has non-zero Gaussian curvature. And the conjecture says that for large enough n, you do have what I earlier called equi-distribution. So the L2 norm on that surface, as n increases, is comparable to the L2 norm of the sequence. So notice that there should be no dependence in these implicit constants on the sequence, but also no dependence on n. Why do you need to take n large enough depending on the manifold? Because you can always cheat. You know, if you want this to happen for all the n's, then for a fixed value of n, you can pick the manifold that contains the zero set or sits inside the zero set of the exponential sum, and then, you know, zero cannot be larger than the L2 norm of a sequence. Why would people be interested in such questions? Well, for many reasons. I'll give you a more obvious reason. Here's an immediate consequence of such a conjecture. This conjecture is true. This consequence is known, by the way. The conjecture is open in most dimensions. So the consequence is known, but it's good to illustrate the relevance. It says that assuming the conjecture, any fixed curved hypersurface cannot lie inside the zero set of eigenfunctions associated with increasingly large eigenvalues n. Okay, because otherwise, again, you'd make the right hand side zero, and it would violate the fact that the sequence is non-zero. Curvature. Okay, that's a key word. Not only this talk, but in most of my work, we do use curvature of these manifolds. What's the relevance of curvature in this context? Well, for this conjecture, obviously the curvature is needed at least for one of the inequalities, actually for exactly one of them, because if you look, for example, this is the case what d equals 2, this sequence of eigenfunctions, the Laplacian have eigenvalues, you can compute them what, 4 pi squared and squared, and they do vanish on this hypersurface. It's a line, it's a hypersurface also in two dimensions, x1 equals 0. So these eigenfunctions are associated with the larger and larger eigenvalues. Nevertheless, they vanish on the zero curvature line. So this inequality cannot be true in the absence of curvature. But curvature is expected to fix the problem. And what's the context?
By the way, there is a very interesting question, even in this case, on restricting to straight lines on the flat torus.
On the next slide, Peter, I was going to mention it. Good to hear back from you. But
Yeah.
let me add that on the
Okay,
next
all
slide.
right. I'll shut up. Okay.
Very good. Stay tuned. I'm getting there. All right, so the general context, which I'll only briefly mention here, is this work of Bourdieu and Svetkov. And they prove that if you have an arbitrary manifold M, two-dimensional, without boundary, these two inequalities hold true. So these are inequalities that compare the L2 norm on the manifold on the right-hand side with the L2 norm on the hypersurface lying inside that manifold. And these bounds are actually sharp, lambda being the eigenvalue, square root of the eigenvalue. They are sharp in general. They are saturated by the sphere. But as it's typically the case with such inequalities, one expects to get better estimates when the manifold M is non-positively curved. So if the curvature is less than or equal to 0, the torus is one such example, 0 curvature, then one expects stronger estimates. And indeed,
just a small remark, this bounds are due to Hermander. For Gerard and Svetkov proved LP bound.
you might be right. Okay, I'll have to go with your expertise.
No, I don't agree with that. Hermander proved it for an infinity, but not for restriction.
Restriction.
He didn't do restriction. No.
All right,
Restriction.
very good. Good remarks.
Let us vote.
So interestingly enough, Bourdieu and Rudnick proved these conjectures. D equals 2 and D equals 3 is, are the cases when they managed to come up with the full resolution. D equals 2 is fairly easy. It is about the number of lattice points on big circles, on some arcs of big circles. There's a beautiful theorem of Jarnik that tells you that a certain arc, well, all arcs of a certain length on circles of big radii contain at most, I believe, 2 or 3 points, lattice points. So anyways, it's at that level. But D equals 3 is complicated. D equals 3 is a 40-page or so long proof that is complicated, but also not difficult to read, and very exciting because it combines a lot of number theory with the Fourier analysis and so on. I'll have that discussion on the next slide. But at the bottom of it is the fact that this being 2, these are all about L2 here. These are L2 theorems. You think L2 is easy. Well, they are easy in some sense. They give you a gate, right? And the gate is just the Plancherel, expand things out, look at the representation using the Fourier transform of the measure. Then what you have to understand is what do these sums look like? Well, if you have a hypersurface, the Fourier transform of the measure supported on that hypersurface has a nice representation as a formula that goes back, I believe, to Hertz or someone in that area. I only have one example here, which shows that if sigma is, for example, the sphere, then there's two components to the Fourier transform. Well, first of all, there's the magnitude, the decay. As xi increases, xi is a subset of R3 or Rn in this case, or D, I should say. The Fourier transform decreases as xi becomes larger, but then there's also an oscillatory term that plays a very important role in their argument, at least in the three-dimensional case. So I couldn't resist, even though my talk is not really about this necessarily, but I couldn't resist giving you an overview of this very, very beautiful argument that they have there, the 40-page argument I mentioned earlier, for d = 3. It's very easy to prove the theorem if you allow yourself log loss. And this log loss would come from just performing easy integration if you only use the magnitude of the decay of the Fourier transform. But now you want to incorporate, of course, the oscillatory term. So there is some exponential sums that arise in the process. And the first ingredient they have is something that quantifies the distribution of the lattice points on the sphere. So if you look at the sphere of radius square root of n, we know from number theory that there are roughly square root of n, well, times n to the epsilon lattice points on that sphere, but they are distributed in bizarre ways. And what you want to do is you want to capture somehow the limit, the extent to which this distribution could be regular by covering the sphere with the caps. So we have here roughly n to 1/2 caps, each with this kind of a diameter. You expect in a perfect world, every such cap to contain one point, one lattice point. Well, it's not the case typically. But then the next best thing that you can do is you can hope that the sum of essentially 1 squared or almost 1 squared gives you back n to 1/2. Again, you hope that this is 1 all the time. If it were, then you'd have n to 1/2, but it's not 1 all the time. Sometimes it's 0, sometimes it's n to a power. Well, in average, things are fine. Then there is a normal form representation for the oscillatory part. This amounts to applying an analytic change of variables to the sphere. And this completely ruins the nice lattice structure of the lattice points on the sphere. You think that you lose all the information by applying this transformation. However, what these transformations preserve is a certain minimal separation between points. So the points don't get too clustered. They kind of keep their statistics, if you wish, in a certain sense. But the algebraic structure coming from the lattice structure, if you wish, is completely destroyed. And then they reduce things to a certain exponential sum estimate, not surprisingly, because of the role of the oscillatory part. Again, listed the power saving result that they have here. These points are no longer lattice points because of 2, they are just separated. It's not a difficult result, but it gives you the flavor of what they need. Okay, now I want to challenge you with something here. Their argument in 3 dimensions, as I said, doesn't quite use the full strength of the lattice points. And what they prove is something more general, namely that you have any collection of points on the sphere, not necessarily lattice points, that satisfy this distribution property, then the L2 result holds true the same way as before. They also make the point that the lattice structure is needed in higher dimensions. I think there's an example in dimension, I forgot, 9 and higher, that shows that no, this approach cannot work. And you have to use periodicity, you have to use something about the lattice points that hasn't been used before. And now back to Peter's remark. Peter made the observation that if you look at the same problem where sigma, so in 2 dimensions this time, where sigma is a geodesic line in the torus, then proving the same estimate in this 0 curvature case is equivalent with the following open beautiful conjecture number theory, which says that each arc of length square root of r on the circle centered at the origin of radius r has to contain at most, well, a uniform number of points, right? So the upper bound should be independent of all. And for smaller arcs, this problem is known. There was a preprint, by the way, that claimed the proof of this conjecture about 2 years ago or so, but then a mistake was found, and in the end, it's you know, at the level of a hopeful approach. I don't think anybody has a proof of this conjecture. Okay, so this gives you an idea that for these exponential sums, if you want to get to the bottom of the problem, things could end up being rather number theoretic. I'd like to look at the next example, the Weyl sums, because in this case, as you might recall, Jean, Larry, and I proved the Vinogradov mean value theorem using Euclidean harmonic analysis and not using any number theory in our argument. So that makes it possible to perhaps fantasize about getting more at the level of perhaps pointwise bounds or bounds of manifolds and hypersurfaces in the same way without using number theory. And this is what my talk is going to be about. Even quadratic sums are fascinating. I illustrate that with a recent result by Baker, Chen, and Sparlinski. To look at the quadratic Weyl sums, the Gauss sums, without any coefficients 1. And if you look at E sub alpha, which is the collection of all the points where these Gauss sums are bigger than a certain n to the alpha for infinitely many n, these three guys managed to find the exact Hausdorff dimension of this set. There's a threshold here that regime change at 5/6 that I don't fully understand. But as an example, if you go for alpha with alpha equals 5/2, then this set has Hausdorff dimension 1. And for every x in this set, you have a huge failure of square root cancellation, namely the lim sup of this weighted expression, where you have n to 5/6 instead of square root of n is greater than 1. This is one example that shows how strange the Gauss sums can behave. All right. Now, let's have a look at these Gauss sums restricted to hypersurfaces in R2. So what is a hypersurface in the two-dimensional torus? What is a sigma? It is of this form. You can parameterize it as an x comma psi of x. You can think about the surface measures being dx, right? We identify the graph with the interval 0, 1. And it's very easy to prove that if psi is C2 and curved, so for example, if psi of x is x squared, that's semi-curved everywhere, then you do have square root cancellation in L2. And L2 turns out to be, again, the correct exponent in 2 dimensions. However, what I proved recently is the fact that there's a huge failure of square root cancellation if you lose curvature. So if you look at x to the k, when k is at least 3, second derivative of that is 0 at 0, and that point, the nearby region, is enough to ruin the beautiful square root cancellation that you have here. So this result is sharp. So it's an upper bound that you can prove using TT-star methods, but it's also a lower bound that arises not for the constant sequence. If you plug in 1 here, you do get square root cancellation. You can use a little bit of number theory to actually prove a bound of 1 here. The terrible sequences again that make that saturate this inequality are a bit more complicated. They are higher order modulations of what I call block sequences. So this is a first example that shows you that curvature actually plays a role for Weyl sums. Curvature, or the lag thereof, in the case of sigma, is very critical. And I'll have a few more examples. Then with my postdoc, Bartosz Langowski, we made a conjecture, which I list here. And the conjecture says that if you have the Weyl sums in the dimensions, okay, so on the one hand, we have the Vinogradov mean value theorem, we know what happens globally, but then if the hypersurface has non-vanishing Gaussian curvature, something like this should happen. So square root cancellation should hold precisely in the range between, well, 2, let's say, and p sub d minus 1. So this is a drop, dimension drop from PD to PD minus 1, which superficially makes sense. You are replacing the d-dimensional torus with a d minus 1 dimensional manifold. Okay, so this explanation is a little bit naive, perhaps, but at least gives you something to chew on. So this is the conjecture, and we believe it's true. And we actually proved it in 3 dimensions. Well, in 2 dimensions, I mentioned it's a fairly easy result. In that case, the exponent is 2. So I talked about the weighted Gauss sums. This is a little bit more difficult, but not super difficult either. And I would like to explain to you why 6. Why can't you go beyond 6? Why can't you put 7 here or 6.1 or anything like that? This inequality is supposed to happen for all curved manifolds, all curved hypersurfaces in tau 3, in T3, in the 3-dimensional torus. And I want to test this inequality actually with a hyperbolic parabola. It's parameterized by x1, x2, x1, x2. This one as a hypersurface has 2 principal curvatures. One of them is positive, one of them is negative. You probably drew the graph of this manifold a few times. If you taught calculus, looks like a saddle, right? And it's doing a lot of damage in the sense that you can work with constant coefficients. You can realize what we call constructive interference on a large set. What is constructive interference? Well, it's the case when all the exponentials are aligning each other in a way that the sum is comparable to the sum of the absolute values. This is as large as n. Where exactly? Well, when x1 is small, x2 is small, and because you live on this hypersurface, that forces x3, which is x1, x2, to also be small. How small? Exactly like this. You plug that into this equation, you're learning that the exponential sum is roughly n to the p on a set of size 1 over n times 1 over n squared. You compare that with the L2 norm to the power p. That tells you that this inequality actually cannot hold for p greater than 6. All right. How do you prove the conjecture? Well, the first time you look at these problems, they look very hard because you integrate on a singular manifold. So what are you going to do? Well, it turns out that you can look at the Fourier transform of the surface. And in the case 1d equals 3, I already had this on the slide somewhere. If we use the decay of the Fourier transform, which is roughly 1 over c, you can transform the problem, right? So essentially you are using the Fourier transform, you get on the Fourier side, you analyze the Fourier transform of the measure, you say, I'm happy with learning just using how rapidly the measure decays without using the oscillatory part. And then if Fourier invert back, you come on the spatial side again. The next thing you know is you no longer integrate on a singular manifold, you integrate now on a cube. We call that a box estimate. So the box estimate is a global estimate where you replace the torus with a smaller piece, but smaller in measure, not smaller in Hausdorff dimension. So from hypersurface, you go back to full Hausdorff dimension. And so you're left with proving this estimate that's in the center of the screen. And I mentioned earlier that one of the things in my work is trying to run away from number theoretic methods. You know, I like proving things that perhaps look interesting to number theorists, but not by using number theory, in part because I don't really know number theory. So here's one example. This estimate, I know it's hard to digest, well, don't try too hard to digest it, but I can tell you that this would follow right away if you had at your disposal something that's very difficult. These are the cubes. I know Peter likes this problem. He challenges many people to actually solve this problem, and there's no progress as far as I know for the last how many decades. So a L6 estimate.
Actually, Victor Wang, a recent student of mine, resolved it under many conjectures, Riemann random matrix theory, and things like that, but very conditional, but on things that are quite independent. So there is a bit of progress.
Okay. That's good to hear. But I think in this case, unconditionally, the best that's known is probably n to the power 1/2 in L6, just to give you an idea about how far things are from n to the epsilon. So in any case, if you knew that, then you could solve the whole problem. We bypassed that, we use decoupling theory. Why is this problem hard? I thought it would include just some computations. This is about the number of representations of integers as sums of cubes.
Let me ask you a question. Yeah, sorry. Suppose I knew, so the progress that I was mentioning, which is of course very conditional, is on the very bottom line, counting the number of solutions to sum of 3 cubes equals the sum of 3 cubes in a box, which is your case with an equals 1. You don't know a relation. I mean, if I knew the case with 1, you wouldn't know it with an, right? Is that correct? You don't know how to reduce. I mean, your case would imply that, but not the other way around. In other words, the number theory will not give you anything with arbitrary coefficients.
Yeah, I think you're right. Yes, it's the restriction problem, which usually involves more work. You're right.
Okay, thanks.
So I'm illustrating here the case of coefficients 1. And let's say we allow also negative choices of parameters here. So we could think about this as going from -n to n. 3 can be represented fairly easily like this. Can you guess the next solution? Don't try too hard. This is the next thing that has been recently discovered. Next representation of 3. I think this gives you a sense of how difficult things can be proceeding, via this approach. Right. So for cubic Weyl sums, we did L6, and that wasn't too complicated. But we also have some results in higher dimensions that are far more complicated, the proofs. For example, in dimension 5, we managed to prove square root cancellation up to 18, and we're short of the ultimate exponent 20, by only using the decay of the Fourier transform. So here I integrate with respect to a singular measure. I don't need to know that this measure is even supported on a hypersurface. All I need to know is that there is a certain decay that a hypersurface would give you. We're not being able to use the oscillatory part of the Fourier transforms a la Bourgain-Rudnick. It's more complicated in spaces like L18. In their case, that part was, let's say, if anything was easy in their argument, was the fact that they work with L2. L18 is way more challenging. I don't think this is the correct approach, but it gives you something that's almost sharp. Again, curvature is important in some mysterious way that I don't fully understand. I'm giving you yet another face of this story. The result with my Postlog that I mentioned earlier can be also reformulated like this. Here's the moment curve, the cubic moment curve, and you're restricted to a hypersurface which has non-zero Gaussian curvature, which amounts to the fact that the Hessian of this third entry is non-zero. In that case, you have the square root cancellation, with the sharpness of L6, but I'm recapping what I said, the sharpness being demonstrated by XY. But then if you change the hypersurface and introduce something like XY, comma, y plus x cubed, things are terrible. This surface, it's hard to tell, doesn't have non-zero Gaussian curvature. There's a certain curve on it where the curvature is zero, and all the points near the curve, are points where the curvature is very small. It's enough to ruin the squared cancellation. Moreover, to make things even more interesting, XY, so the hyperbolic, parabolic, 6 is the limitation, but if you write x squared plus y squared as the elliptic paraboloid, we believe that you can go all the way up to L7. And I can tell you that for that problem, Euclidean harmonic analysis in itself is not enough. That problem looks very number theoretical, right? So getting to L7, I don't know how to approach that problem, but curvature is important. And this begs the question, and I'm going to end with this slide. Is it possible that for the Bouguin-Rudnick problem for the Laplace eigenfunctions, curvature is also critical? So I mentioned Peter's reduction of this conjecture in the case when you have zero curvature line, the reduction to this difficult number theoretic conjecture. There's probably similar reductions in higher dimensions that I haven't worked out. But because of all these examples that I showed you earlier for the Weyl sums, where curvature is important, because of those, I start fantasizing that perhaps curvature is also important here, and perhaps all these conjectures about lattice points, the uniform uniform upper bound of lattice points on small arcs or small caps, perhaps they are not true for some reason, or if they are true, it must be because of a higher reason. Peter will know that all these conjectures for the Laplace eigenfunctions on the torus are part of a more general mathematics for manifolds with non-positive curvature. So there may be a much deeper sort of mathematics and reason why such theorems are true. Bouguin and Rudnick used Fourier analysis because those seem to be the tools on these manifolds, but maybe there's a higher level of mathematics that would address questions in a much more general framework. I don't know. These are all good things to think about. All right, thank you very much. That's all I have in mind.
Are there questions?
If I can ask one.
Yeah.
There's a problem I think you and Bouguin thought about, and I can't remember, and you must be revisiting it. So instead of the moment curve in 3 variables, you look at the thing that gives a sum of 3 cubes equals a sum of 3 cubes in a box, and a linear equation, but you don't put the quadratic one. So if you put all 3, sum of 3 cubes equals sum of 3 cubes, sum of x1 squared plus x2 squared plus x3 squared equals y1 squared plus y2 squared plus y3 squared, and then the linear equation, that's your Vinogradov mean value theorem. Maybe even Vaughan proved it in that case, I can't remember. But if you just take 2 of those equations, so you were mentioning before, if you just take sum of 3 cubes equals sum of 3 cubes, that's of course problematic. There is some work of Woolley and Vaughan which analyzes this intermediate, and I think do you have a much more general theorem with ANs which implies that? I think that you and Bouguin told me that. Is that written up somewhere? Do you know what I'm talking about?
No, so they have so for TT cubed, the critical exponent is L8. So you have linear and cubes, 2 equations.
Yeah, exactly.
L8 would be the critical exponent. If you prove L8, you prove everything. L10 is, I think, what decoupling could give. I think we probably have that in our papers, but Woolley managed to do it for L9 for constant coefficients. And then Kevin Hughes, student of Eli Stein, proved it recently, maybe with Woolley for arbitrary coefficients, but it's still L9. As far as I know, there's no progress on that problem beyond L9. You're right, it's easier than just the cubes, perhaps much easier, but still outside the scope of what I think decouplings can do.
Okay, thanks. I'll look that up. Thank you very much. And great lecture, by the way.
Thank you.
Are there any more questions? Thank you, Ciprian, again. Thank you.